Now let's look at the velocity expression in the two-dimensional motion. So again I will draw the coordinates over here, no sorry, the coordinate axis over here like this. These are the two coordinate axes, x and y, and I have a particle here, okay, which has a position vector of r1 bar, position vector of r1 bar, and after some time it reaches here, and let's say the position vector becomes r2 bar, right? Now if we assume that this particle is moving with a constant velocity, let's say the velocity is v bar, okay, this is the velocity of the particle. So this is constant velocity, okay, this is the constant velocity, uniform velocity. Then what is the velocity expression that I can write in terms of the position vectors? So now what will be the velocity? Velocity is equal to displacement by time, right? Velocity is equal to displacement by time. So displacement is what over here? Displacement is nothing but the final initial position is this one and final position is this one. So the line joining the final position and initial position, that is this particular line, is the magnitude of the displacement, right? And this displacement vector will point from initial position to final position. So this is a vector in this direction. This is your displacement vector, let's say s bar. Now s bar will be r2 bar minus r1 bar. So if I apply a triangle of vector addition over here, so r1 bar plus s bar will be r2 bar. So s bar will be r2 bar minus r1 bar. So this is the displacement. So this displacement divided by the time will be the velocity. So the velocity over here can be written as v bar is equal to r2 bar minus r1 bar, that is the displacement, divided by time. Let's say the time initial position, when the particle was at initial position I, the time was 0, and when it reached to the final position, the time became t. So in time t it reached that position. This implies we have v bar t is equal to r2 bar minus r1 bar. So if I take r1 bar to the left side, what I will get? r1 bar plus v bar t is equal to r2 bar. So if I rearrange this like that, okay, so I get this. So now this will look familiar to the equation that we have already used in one-dimensional motion when I write it in terms of components x and y. So if I write it in components, r2 can be written as x2 I cap plus y2 j cap is equal to x1 I cap plus y1 j cap. Here this x2 and y2 are the components of the r2 bar vector, x1 y1 are components of r1 bar vector, and vx vi are the components of the v bar vector. So if I combine this, okay, so if I combine the right hand side, okay, for the I cap, so this will be x1 plus vx times t I cap plus y1 plus vy times t j cap, okay. So I can infer from here that this x2 must be equal to this, and this y2 must be equal to this, because these are ith and jth components. So x2 will be, so here x2 will be equal to x1 plus vxt, and y2 will be equal to vy t, okay. So this is the equation. Now note that what does this equation, these two equations suggest, okay, what these two equations suggest. If I rearrange this equation, okay, this first equation will look something like this, okay, x2 minus x1 divided by t is vx. This is nothing but displacement in x direction divided by the time, which is the velocity in x direction. And similarly for y direction, this is y2 by y2 minus y1 divided by t is vy. So this velocity in y direction and this velocity in x direction is nothing but the displacement in x direction divided by time for vx, and for vy it is displacement in y direction divided by time. So these two directions can be thought of as independent of each other. So the velocity in x direction does not depend on the velocity, on the displacement in the y direction, okay, and the velocity in y direction does not depend on the displacement in x direction. So these two directions can be thought of as independent of each other, okay. These velocities do not depend upon the another direction's displacement, okay.